Hello, we are from group G2C, and this is the production of cumin via alkylation for IDP Project 2026. So this is our team, and this is the process flow diagram that we came up with. It has two stages. The first stage is the reaction stage, and the second stage is the recycling of benzene. And we have all of these units in our process flow diagrams. The main thing here is the reactor and the distillation columns. Next, this is the main reactions that is happening in the reactor.
Assalamualaikum ingredients. My name is Fatin Shaira binti Fashar. Firstly, as part of our cumin production plant design, we have to do the mass balance, and it is very crucial. So our objective was to quantify every stream variable, including molar flow rates and compositions. So I'll begin with the non-reactive system, focusing on distillation column 2. So the goal here is to separate pure cumin from the heavier byproduct PDIPB. So this is our assumptions. The first one is taking a basis of 100 kmol per hour for the feed, and the second is the feed is strictly composed of 96.8% of cumin and the rest is DIPB, and the third one is the bottom stream has 100% of the PDIPB, and the fourth one is recovered DIPB is reused in the transcirculation reactor. So this is our calculation. For the first one, we do the basis and DOF with two underflow rates and two independent equations. Our DOF was exactly 0, confirming the system was solvable. So the step 2 is using a basis of 100 kmol per hour for the feed, doing over mass balance, and the third is component balance. We achieve 100% recovery of cumin in the overhead stream. So the fourth one is mass conversion. So this is our results: molar flow rate, mole fraction, and mass fraction. So the overhead product reached a high purity of 99.9 mole% of cumin, while the bottom stream successfully constructed the PDIPB for recycling. So next is the reactive mass balance for our alkylation reactor by focusing on conversion of raw materials, which is benzene and propylene, into cumin. So we have two reactions. The main reactions is benzene react with propylene to produce cumin, and the side reaction cumin react with propylene that produces andesite PIDIPB. So this is our assumptions. The first one is the feed input consists of 100 kmol per hour of propylene, benzene, and DIPB. And then the second one is total conversion. Propylene acts as 100% single pass conversion, and the high salinity 16/1 efficiency ratio. And the fourth one is specific yield. For every 17 moles reacted, 16 moles yield the target product. And this is our calculation. The first step is the molar balance, which is the input plus generation equals to output plus consumption. Then we apply a 16/1 selectivity ratio using the extent of reaction method for step 3. And the fourth is finding the yield. This resulted in a cumin yield of 88.89% based on the limiting reactant propylene. So this is our results. So I verified the total mass flow, showing that our input of 7081.6 exactly match our output. So this high yield proves that our reactor conditions are optimized for the desired product. So this is our results for overall molar flow rate, mole fraction, and mass fraction.
Hello everyone, my name is Siti Nurfaiza binti Bacho, and I'll be explaining the energy balance of both units. So for the first one, for non-reactive, we choose distillation column 2. So the only difference here, we have to consider the temperatures and pressures coming in and out of the system. And we have to pick a reference state. In this case, I chose the inlet stream as my reference state. And then after that, we can complete the table by finding H and N. How do we find specific enthalpy? So the way we find specific enthalpy is to form a hypothetical pathway, and then we have to consider the change in temperature. We use this equation, and we use this equation for change in pressure. And if there is any change in state, then we consider the heat of melting or heat of vaporization, etc. And then we form this pathway and we solve it. After that, we just insert all of the information that we already calculated into the general energy balance, and we know that there's no kinetic energy, no potential energy, and no work shaft done. So our H enthalpy will equal to heat gain or loss in the system. For the next part, for reactive unit, we have the reactor. So for reactor, we have to consider the two reactions that is happening inside of the reactor, which is the formation of cumin and the formations of DIPB. And first of all, we have to choose a reference state. In this case, I chose my inlet upstream again as my reference state. And then from the previous calculation, we saw that the effect of change in pressure is very, very little. So in this case, I assume it as negligible. And then we complete the table by finding H and N. After we solve that, we can find the extent of reactions and stated heat formations. But in this case, we have to consider for each of the reactions separately. So we solve separately for for stated heat of formations and reaction extents for cumin and the IPB, and then we sum both of that and just insert that in the general equation right here, with the only difference having this extent of reaction and heat of reactions. And then we can cancel this out because our molar coming in is 0, so we can cancel this term out, and we solve. This is the heat gain or loss in the reactor. In this case, it's exothermic.
For my part, I'll be presenting the fluid mechanics analysis in the cumin production pipeline system. In a chemical plant, many material must be transported between different units like reactor, separator, and distillation column. The diameter of the pipe play an important role in determining the flow behavior. Smaller pipe diameter will increase the velocity of the fluid, while larger diameter help reduce friction loss and pressure. To simplify the fluid mechanics analysis, several assumptions are made. First, the flow is assumed to be steady flow. Second, the fluid is assumed to be incompressible. Third, the flow is assumed to be one-dimensional. Fluid is treated as a Newtonian fluid. Different pipe diameter are selected for different stream. Fluid viscosity value used in the calculation are taken from literature data and operating temperature. The pipeline are assumed to be made of stainless steel. Pipe length are assumed to range from 3 to 12 meters. Shorter pipe length help reduce friction loss and improve the efficiency of the pipeline system. Several additional assumptions are also made for energy balance in the pipeline system. For the pumping system, pump power is assumed to be 10 kW with a pump efficiency of 80%, which is suitable for medium-scale industrial fluid transportation. Several calculations are performed to analyze the fluid flow in the pipeline. First, the mass flow rate is calculated using the molecular weight and molar flow rate. The volumetric flow rate is obtained using the density relationships. The velocity of the fluid is calculated using the pipe cross-section area. The Reynolds number is determined to identify the flow regime, which helps us obtain the friction factor for the pipeline. After obtaining the flow property, several important equations are used in the analysis. These include the total friction loss equation, the work of the pump, and Bernoulli equation. Bernoulli equation helps us analyze the energy balance between different points in the pipeline. Finally, pressure drop for each pipeline is summarized in a table. This table shows the calculated pressure losses for all the pipeline in the system.
Okay, now I'm gonna explain about the strategy for delivering the main product. For fluid transport system, the final product, which is cumin, from the last distillation column is transported to the storage tank through a pipeline system. The pipeline is designed and using a fluid mechanics principle to ensure steady flows and minimize pressure losses. The movement of the fluid through the pipeline can be analyzed using the Bernoulli energy balance. You can see this is the formula. The fluid flow is analyzed using the Bernoulli energy balance considering pressure energy, kinetic energy, potential energy. There's energy losses occur due to pipe friction and fittings such as valves, bends, contractions, and expansions. These losses are known as head losses and must be overcome in order to maintain the desired flow rate throughout the pipeline. Next, to ensure continuous and stable transportation of the product stream, a centrifugal pump is installed to overcome pipeline friction losses. The pump provides additional mechanical energy to maintain the required flow rate. Next, the pump power. The pump power is estimated using this formula. P equal to rho GQH over efficiency. P is pump power, rho is density of the fluid which is cumin, G is the gravitational acceleration, Q is volumetric flow rate, H is the total heat required to overcome friction and elevation differences, and this symbol is the pump efficiency. After we substitute the value, we will get P equal to 10 kilowatts. This value is within the typical operating range for a centrifugal pump used in liquid transfer system in chemical process plants. The selected pump provides sufficient energy to overcome pipeline losses while maintaining stable operation and ensuring continuous delivery of the product to the storage tank. Next, based on the estimated production rate of the chemistry, the storage tank with an approximated capacity of 100 meter cube is considered suitable to accommodate the production output while providing operational buffer capacity. A cylindrical vertical storage tank is selected due to its structural stability and efficient use of space in industrial plant. We will use the diameter of 4 meter and height, which is 8 meter, to maintain practical construction dimension.